We, the scientists, have eagerly awaited this moment for over a century, since 1916. A moment that once seemed almost too distant, too unreal. But after all the years of anticipation, we now find ourselves standing on the brink of a groundbreaking revelation in the world of astronomy. The photograph we've all been waiting for has finally arrived, more than 30 years after the mission first took shape. On Christmas Day, 2 years ago, the James Webb Space Telescope, JWST, a feat of modern engineering, was launched from French Guiana. Its journey through the cosmos was nothing short of spectacular. After a quick but awe-inspiring flyby of the Moon, the telescope fired its engines for a critical 5-minute burn on January 24, placing it into its final orbit 1.5 million kilometers from Earth. From that point, we entered the waiting game, days of fine-tuning and calibrating, as the telescope began its mission of observation. Finally, on July 12 of the following year, it delivered the first image, a breathtaking glimpse into the distant universe, revealing galaxies as they appeared more than 13 billion years ago. Since that historic moment, the James Webb Space Telescope has continued to expand our understanding of the universe. Every new image adds another piece to the puzzle, and it's becoming ever clearer, we are witnessing the dawn of a new era in space exploration. But with these revelations comes something both awe-inspiring and sobering. These photographs serve as a stark reminder of both humanity's extraordinary capacity for discovery and the humbling fact that we are infinitesimally small in the grand scheme of the cosmos. As we begin this exploration, we invite you to dive into the latest images captured by the James Webb Space Telescope. These aren't just remarkable scientific observations, they are windows into the very fabric of the universe. When we look at the night sky, it's easy to assume that telescopes are peering back in time. But that's not exactly how it works. Telescopes don't provide a direct glimpse into the past, it's far more intricate than that. The light we see from distant galaxies isn't a time capsule, but rather a snapshot frozen in its journey across the universe. The light that reaches us from these distant places has been traveling for millions, even billions, of years. As it makes its way to Earth, that light retains its pattern, like an old photograph. What we are actually seeing is the light as it appeared when it was first emitted. Imagine, for a moment, that you have a photograph of your daughter as a child, and years later you look at it. In one sense, you're looking back in time at what she once was, but you're not actually seeing her as she is today. The image you're looking at reflects the past, but it's not an active window into it. In much the same way, the light from distant galaxies doesn't show us the present, but the state of the galaxy when the light first left it. Think of it like this: what if a spill of ink accidentally created a mark on that photograph? You might think there was something unusual happening at the time, like a UFO or an electrical storm. But that would be a mistake. The mark you're seeing today is a product of what's happening now, not of the moment captured in the image. Similarly, the light from galaxies might have been altered by cosmic forces, but the pattern we see today is still a reflection of what it once was. How, then, do we uncover the secrets of these ancient cosmic photographs? The answer lies in a phenomenon known as redshift. As the universe expands, the light from distant galaxies stretches out, making it appear redder than it would otherwise. The redshift serves as a cosmic time stamp, enabling us to calculate how far back in time the light originated, and piece together a picture of the galaxy's history. With the James Webb Space Telescope, we're now able to observe galaxies that are over 13 billion years old, some of the very first to emerge after the Big Bang. This treasure trove of galaxies, explored by the JWST Advanced Deep Extragalactic Survey, JADES, reveals stunning new insights about the infancy of the universe. The study focused on two overlooked areas of the sky, near the Fornax cluster and the Ursa Minor constellation, finding over 700 galaxies previously undetected, providing a clearer view of the universe's formative years. If we were to condense the entire history of the universe into a 2-hour film, these galaxies would appear in the opening minutes. Kevin Hanline, an assistant research professor at the Stewart Observatory, explains that these galaxies offer a rare look into the very early stages of cosmic development. They were not just scattered clumps of gas and dust, they were the building blocks of what would become the vast and complex cosmos we observe today. As we venture into the early days of galaxy formation, we discover that these galaxies were far more complex than we once thought. They weren't simple blobs of matter, but fully formed structures with visible features and ongoing star formation. This discovery marks a huge leap forward in our understanding of early galaxies, something we could only dream of before the JWST. In the past, the early galaxies we observed appeared as faint, indistinct smudges of light. But with Webb's cutting-edge technology, we're now identifying galaxies thousands of light-years wide, bursting with life and activity. Nearly 93% of the galaxies uncovered in this study were completely unknown until Webb's observations. Even with previous telescopes like Hubble and Chandra, these galaxies remained hidden in plain sight. The universe is far from static, and as we shift our gaze, we're finding more than just rare anomalies. We're diving deeper into the most common galaxies, the ones that make up the majority of the universe's mass. How did the chaotic, dense, and dusty universe we see today transform into the transparent cosmos we observe now? One theory suggests that the transition from opaque gas clouds to a clear universe began with the epoch of Rayonization, roughly 400,000 years after the Big Bang. During this era, the first stars formed, releasing ultraviolet radiation that Rayonized the universe. As we continue to study these galaxies, astronomers are investigating the role of supermassive black holes and their potential influence on cosmic evolution. Could these giants of the universe have been more significant in shaping the cosmos than we ever realized? Thanks to Webb, we're beginning to uncover new layers to this mystery. In another groundbreaking study, researchers are examining galaxies formed between 500 and 850 million years after the Big Bang. In the context of our 2-hour film, these galaxies would appear in the first 5 to 8 minutes. They were chaotic, yet their formation played a key role in the process of Rayonization. By analyzing the light emitted from these galaxies, astronomers are learning more about the dynamic forces that shaped our universe. One of Webb's most exciting capabilities is its ability to capture gravitational lensing, a cosmic optical illusion that occurs when massive galaxies bend light from galaxies behind them. These lensed galaxies reveal new clues about the distribution of mass in the universe, allowing us to see things we would otherwise miss. In addition to exploring distant galaxies, Webb is also taking a close look at exoplanets much closer to home. One example is WASP-18b, a gas giant with a scorching atmosphere that reaches 5,000 degrees Fahrenheit. Even in such an extreme environment, Webb detected water vapor in its atmosphere, an astonishing discovery that highlights the telescope's extraordinary precision. Contrasting this fiery world is another exoplanet, VHS 1256b, where violent sandstorms rage across a landscape of blistering temperatures. Despite the planet's hostile conditions, Webb detected methane and water vapor in its atmosphere, underscoring the telescope's remarkable sensitivity to even the most extreme environments. The discoveries from the James Webb Space Telescope continue to redefine our understanding of the cosmos. Every image, every data point,